If you've been watching the syllabus, we will not be covering section 10.3. So today we'll do 10.4, which is dependent samples. And the reason we don't do 10.3, remember when you go into the calculator to do a 2-SAMP t-test, there's that question you have to answer. Pooled, yes or no? And I said what?
No.
Always say no to the pooled question. Well, 10.3 is what you do if you want to say yes to that question, right? But as I said before, there's really never a reason to need to do that, because by saying no, even if the two standard deviations are the same, you still get the same results. So there's no real reason to cover that section. So today is section 10.4, which deals with dependent samples. And you remember what we said that meant? What does it mean to say two samples are dependent?
They affect each other?
Okay, they affect each other, or maybe it's not so much they affect each other, but there's some relationship between them. Okay? Knowing something about a value in the first sample, if that gives you information about a possible value in the second sample, then they're dependent. Okay? And what did I say usually is the case for dependent samples?
The same subject.
If it's the same subjects. And I talked about giving you a pre-test and a post-test. So you'll see lots of examples in section 10.4, both in the book and on the homework, where you have two measurements made on the same person, like a before and an after. Maybe it's on placebo and then on active drug, or whatever. But it's two measurements made on the same person. That tells you it's dependent samples. And then typically, these are referred to as paired samples. So by the word paired, we're kind of emphasizing that there is a measurement that exists in the first sample that can be matched up to a measurement in the second sample. So if I give you a pre-test and a post-test, I can pair your two observations together because they came from the same person. Okay? So comparison of two means in dependent samples is a little bit different. Now, before I go any further, in this section is comparison of two means and comparison of two proportions. He did both means and proportions in one section, and it's too much. So there's a really good chance that I won't get to the proportions part of it. And since we're pretty much out of semester, that just means we aren't going to do it. I won't come back and do it another day because I don't have any days left. I've already got things I need to do on those days. So if I don't get to proportions, I'll just go into the online homework and pull out the proportions questions before I assign it. I've actually already assigned it, I guess. It's already out there and ready to be used, but if that, I'll switch it. I'll delete those questions out of it. Okay? So we're going to talk about comparison of two means from paired samples. Okay? So just like when you had two independent samples, what's of interest is the difference between those means. Okay? So a null hypothesis could be written like that. Just like before. It looks exactly the same. There is no difference. The difference is zero. That's the null hypothesis. But now, what we're mostly interested in is the difference. So we take the differences within each pair. And then we analyze as one sample of differences. So I can revise my null hypothesis with a little bit of different notation to be that. What do you suppose that little sub D means? differences. So what it's saying is the mean difference is 0. This is a difference of two means. This is the mean of differences. Right? So difference of means, mean of differences. Is that the same thing? Well, we'll talk about that more. It can be the same thing. When you have paired samples, they are the same thing. So those are equivalent hypotheses. The alternative hypothesis is that the mean difference is not 0, or is less than 0, or is greater than 0. But almost always, this value is going to be a 0. Now, always is a strong word for a statistician to use, so I should say almost always. It's fairly rare that you want to check to see if the difference was a certain amount. Is there a difference of at least 5 or something like that? It's usually, is there a difference or not? Okay? So almost always that value will be a 0. Okay? Now, to motivate this, we're going to do a little activity in here. Okay? We're going to design an experiment. We've been talking about heart rate a lot. Last time in class we did 2 sample t-tests to check for differences in heart rate between smokers and non-smokers. Remember doing that? And what did we find? There is a difference. We found a statistically significant difference in the resting heart rate between smokers and non-smokers. What about exercise? We looked at that also. And there was also a statistically significant difference. I don't think I had time to get to males and females. Did we do that one? Okay. But if you do, I had the data for it, we just didn't get to it. But on that one, you would not find a statistically significant difference between males and females. There is no inherent gender difference in heart rate. But let me ask you this question. What about taking your heart rate while you're sitting down compared to standing up? Would there be a difference?
Yeah.
You think so? Are you sure? Or are you just guessing? Why are you sure?
We did it in biology.
Ah.
We took our sitting, lying down, and standing pulses.
And how did they go?
Laying down was lower than sitting, and then standing was higher. That was kind of,
And standing was higher than sitting.
Mhm.
Okay. Why do you suppose that is?
You're using more muscle and energy to stand.
Yeah, it takes more energy to stand. Plus, if I got to pump blood from my ankles back to my heart's got to beat either faster or stronger to do that. Yeah.
It really does. Orthostatic hypertension.
Are you a nursing student?
Yeah.
All right, go nurses. Orthostatic hypotension or hypertension, depending on if it's low or if it's high, right? So what we're going to do is I'm going to take a random sample of, well, no, before I say that, I want you to design me an experiment. How can we test to see if it's different?
Using 2 tests of the same person standing up and sitting down at the same rate.
Okay, use the same person twice, measure that person sitting down and measure them standing up. What kind of a design is that called? Oh man,
Crossover?
chapter 4. Crossover, very good. That's a crossover design, right? What would a 2 independent samples study be like?
one person sitting down, one person standing up, 2 different people.
Okay, 2 different people, and in particular 2 different groups. I could randomize 5 of you to sit down and 5 of you to stand up and measure everybody's pulse and then compare those means. That would be a 2 sample t-test because they would be independent samples, different people, right? Which do you think is the better design?
Crossover,
Crossover, why?
because it's the same person, so it might be different between 2 people altogether anyway. And so if you're using the same person, you can measure the actual difference between whether they're sitting down or standing up, 'cause it's the same person.
And that's exactly right, what she said. She got at several points there, and one of the points is there's more inherent variability or randomness between two different people than there is within a person sitting versus standing. There might be some random variability that, you know, for some reason their heart was a little higher when they were standing than it was when they were sitting, just by randomness, but most of that difference would be because of the physical change of sitting to standing. Right? Whereas from person to person, if I just happen to randomize somebody with a 100 beat per minute resting pulse to my sitting group, and somebody with a 50 beats per minute pulse while they're standing up, and those people do exist, I'm one of them, right? Then, you know, by random chance, you can make it look like, well, there's no difference. But if you put the 100 person and you put the 50 person and do them both each way, what do you suppose would happen with the 50 person when they sat back down? It's probably going to go even lower, right? So whoever's lowest in one sample is probably still going to be lowest in the second sample. Whereas if you do two separate groups, you never get to see that. So every person serves as their own control. Now what we're going to do is we're going to do a crossover study, but we're going to first do what's called a parallel groups study, a two-sample study, and then we're going to convert it into a crossover, and we're going to see, not only we're going to learn how to do paired t-tests in this section, but we're going to learn why one design is stronger than the other. Okay? So here's how we're going to do it. I'm going to take my calculator here, and I'm going to select, I'm going to go to Math, and then PRB, and then down to rand int. Oops, I hit the wrong one. This is a lot easier to do on my real calculator than it is this simulated one because it's so slow. Oh. Don't laugh at me. I'm computer challenged. There. Rand int. That's the random integer, and then I'll give it a starting number and an ending number. But before I do that, I need to know how many people are in here. And I need to give each of you a number. Alright? So what I'm going to do is I'm going to run the room real quick, and I'm going to point at you, and I'm going to say a number. It's your responsibility to remember that number. Now if you have a memory like me, maybe you should write it down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Got it? Okay, now what I'm going to do is I'm going to tell the calculator 1, 18, and hit enter. So person number 11, you're our first lucky contestant. Who's that? Who's 11?
Oh,
That's
sorry.
Wake up. So here we go. So this is subject ID, person number 11. Okay? And now I'm just going to hit enter and get the next one. Person number 2. Who's that? Naomi. Okay. Person number 3 is person number 1. Doesn't sound right, did it? I should. Oh, I got a 1 again. What do we do if we get a repeat? Just ignore it. Do it again. So then I go to 13. That's you. Okay. And let's see. That was 4. My 5th person is 13 again. 16. Okay, Gary. Okay. So these are going to be my sitters. Okay? Now I'm going to get a random sample, an independent random sample of standers. Okay? So here we go. I'm just going to do all 5 of them, then walk over there and write it down. So I'm going to hit clear. And then if I just hit enter again, it should redo what I did. Number 7. Who's number 7? Okay, Chelsea. Number 3. Have I already picked 3?
No.
Okay. Number 9. Is that you? You looked at each other like, you're 9, I'm not 9. Number 18. And number 13 is a repeat, right? So, number 10. Is that you? Well, see, now you're in competition, right? Because you're in the other group. Okay, so here we go. It was 7, 3, 9, 18, and then 10. Okay? So, just so the audience at home has something to look at while this is going on, I want those in the stand group to come stand right up here. Those in the sit group can just stay where you're at. And what I'm going to do is I'm going to say go, and then I'm going to watch my watch for 30 seconds, and then I'm going to say stop, and I want you to count. And those of you that are in the sit group, find your pulse. Those of you up here, find your pulse. And when everybody gives me the nod that they've found their pulse, try not to take too long. You found your pulse? You don't look like you didn't even. Everybody got it? Does everybody sit and have their pulse? Go. Stop. Okay, now you can sit and remember your number and then double it, and that's your heart rate. Okay? All right. Now, let's see. Let's start with the sitters. Who was number 11? What was your heart rate?
80.
80? And number 2?
70.
70? Number 1?
64.
64? 13? Aaron, were you 13?
Yes.
62.
62? And number 16?
68.
68. Okay? Now the standards. You're number 7? What was it?
78.
78. Number 3?
68.
68. Number 9?
94.
94.
62.
62.
82.
82. Okay. Now, what I want you to do is I want you to put these numbers into L1. Nope. Put those into L2 and put these numbers into L1. I want the standing heart rates in L1, and I want the sitting heart rates in L2. And I'm going to do it up here on the screen at the same time. Hopefully you know how to put data in your calculator at this point of the semester. Okay, then I need to put my sits in. I got 80, 70, 64, 62, and 68. Okay? You know what? If I had a longer cord, I could stand over here and hit the buttons. How do I test for a difference between those means? Let's set up our null and our alternative hypothesis. I left my marker over here. I'm calling this group 1 and this group 2, just by virtue of putting them in L1 and L2. Okay? So my null hypothesis is what? The mean. Now this is a independent samples test, right? So this is mu1 minus mu2 equals 0. Now everybody told me before we started this, those that had an idea about it, that standing heart rate was going to be higher. So that's what I want to test. Is it higher? So tell me how to set up my alternative.
M1 is less than M2.
M1, this is group 1.
Or M2. Yeah. So M1 is greater than.
Okay, so what about the difference? If M1, you guys got me saying M. If mu1 is greater than mu2, what kind of values would I expect to get when I subtract? Positive. And positive are greater than 0, right? So the point of going through that is, it doesn't matter which way you do the subtraction, but once you decide which way you're going to do it, then you got to figure out, okay, what direction does my inequality go? And it depends on which you called 1, which you called 2. The most common mistake is to decide here, but then turn that the wrong way. And then you get really strange p-values. Well, if you ever get a p-value that looks really strange, like 0.99993, that's a weird p-value. I'm used to small numbers. Okay, so I'm going to test this. So now go to your calculator and do that test. And you just got tested over this, not very well. No, I guess we didn't test over this, but you had homework over this. So where do you go first?
P-value, or the CMC test?
Okay, you go to stat, then test, then down to two-samp t-test. This is the independent samples test from last section, not this section. So when I hit that, do I have data or do I have stats?
Data.
I have data, so tell it data, and then it's going to want to know what lists your data are in, and it should say L1 and L2. If it doesn't, make it say L1 then L2, because I want my standing to be group 1. And then pick the greater than mu2 symbol, because if I move mu2 over to this side, then I still have the greater. So use the greater than symbol. And then say pooled equal no, and calculate. So you can see that the t-test statistic is t equals 1.25, and the p-value is 0.1276. Okay? Now, Crystal, you're all over what a p-value tells you to do, right? So what's my decision now? Looking at that, what's my conclusion? I want to know, is the null true or is the alternative true? And I just kind of said something wrong. I said the null true. We never can say that for sure, right? So do I reject the null or do I fail to reject the null? You say reject the null? Anybody else?
Fail.
And why? What's the rule?
Bigger than.
If the p-value is bigger than your significance level, which I didn't give you, but so we use 0.05. If it's bigger than that, and you say, well, this says there's a 12%, almost 13% chance that you could get this amount of difference just by random chance. That standing and sitting, even if there's no difference, you could get that big of a difference 12% of the time just by random chance. So it's not strong enough evidence to reject the null hypothesis. So from that study, using 10 people, I don't have sufficient evidence to say that standing heart rate is any different than sitting heart rate. Huh, you were wrong, Chelsea. You told me that it was going to be higher. Ha, you're wrong. Can I say she's wrong? No. I can only say, my study did not find sufficient evidence that she's correct. Right? But we said that this isn't the best design. A better design is a crossover. So if you were sitting before, come up here and stand. If you were standing before, you may remain seated, but find your pulse. See, I make them come up here so that the camera knows there actually are people in this room besides me. Because otherwise, I don't think they ever know that for sure. Now, everybody give me a nod when you found your pulse. Everybody got it? Everybody sitting down? Okay. Go. Stop. Okay, remember your numbers and go double them and write them down. And we'll start with this group that was sitting this time. Person number 7, what was your heart rate?
16?
What? Did you say 16?
60.
Scared me. Man, I killed her. Person number 3, 60. Person number 9,
78.
78. Person number 18,
58.
58. Person number 10,
70.
70. Like that? Okay? Now we'll come over and get this other one. And person number 11, 84. Number 2, 72. Number 1, 68. Number 13, 70. And number 68.
76.
I mean, number 16.
76.
76. Okay? Now, what do you notice about every single pair of observations?
There's difference.
There is a difference, and which one's bigger? Standing. So some would argue, including me, that you really don't need any fancy schmancy statistical test to know standing heart rate is higher than sitting heart rate, because every single person we looked at, their standing was higher than their sitting.
What if one wasn't?
And usually there is at least one that isn't. It's rare that it goes down, but fairly often you'll get a few zeros in there, right? But you just, okay, that's what the data shows. If the null is true, there's really no difference. What would you expect to see by random chance? Zeros and about an equal number of positives and negatives, right? Because your heart rate's going to change. If I checked your heart rate right now, it's probably not going to be exactly the same as what it was when I checked it a second ago. There's random fluctuation. But you would expect just as many positives as negatives and probably a whole bunch of zeros if there really was no difference. Right? But let's do the test. So how are we going to do this test? How do I account for the fact that they are paired observations? Well, what did we say here? We want the mean of the differences. So that tells me I'm going to take the difference within each pair. Then I'm going to worry about those numbers. So I want to do the difference in the same direction. So stand minus sit. I want to compute stand minus sit for each of these. And for right now, we're going to only use 5 observations. So since this one's in the correct order, stand, then sit, let's just subtract this way and get these 5 differences. So let's do them in our head. What's 78 minus 60? 18. And what does that 18 tell me? It tells me that person number 7 was 18 beats per minute higher when they were standing up than they were when they were sitting down. Next person is 8. 94 minus 78 is, I can't do them in my head all the way. 16, okay? 62 minus 58 is 4. 82 minus 70 is 12. I started right 8. Now what I want you to do is I want you to enter those 5 numbers into L3. Okay? Just those 5. We'll worry about these differences in a minute. But for now, just put those 5 differences into L3. And I will do the same. So what were they? 18, 8, 16, and 4 and 12. Okay, I don't think I made any data entry errors. So now, what did I say our strategy was? We compute the difference within each pair, and then we treat it as one sample of differences. So now we've gone from a 2 sample means problem to a 1 sample means of differences. So how did we do 1 sample means hypothesis test? T-test. So don't use 2 samp T-test, use T-test on L3. So just go down to T-test, tell it you have data. What is mu sub 0? 0. Here's our null hypothesis, right? So this is mu sub 0. So I need to change it. Mine says 18. I need to make that a 0. Then I need to tell it that my data is in L3. So I push second function, L3. Leave the freak as 1. And I want the greater than symbol because I guess I never wrote it down. But here's what it is. For the paired, it's mu d equals 0, mu d greater than 0. And then just hit calculate. So for this test, the test statistic T is 4.53, if I go to 2 places, and a p-value of 0.005. Crystal, it's redemption time. What's the conclusion now? Small p-value? You're guessing, but I'll take it. You got the right guess. We're going to reject the null. The p-value says what? That a difference, an average difference, and it'll tell me what the actual average difference was. See the x bar? It says x bar is 11.6. That means on average. If I average these differences, the average is 11.6. So on average, people's heart rate was 11.6 beats per minute higher when they were standing. This says there's only a 5 out of 1,000 chance that you could get a sample with that big of a difference if there really is no difference in the population. So the conclusion is reject the null. There must be a difference in the population because you almost never would see data like we just saw. Okay. So one of our experimental designs soundly rejects the null hypothesis. The other one fails to reject the null hypothesis. One of them's wrong, right? They made different conclusions, so one of them has to be wrong. Which one do you think's wrong, and what type of error was it? Okay? You think this one's wrong?
They failed to reject the null when the null was, false.
Okay, it looks like it failed to reject the null when the null was false, and that is a type 2 error. Okay? Notice how many people did I use to do this test? 5. 5 people. To do this test, 10 people. And often in clinical trials, each patient can be very, very expensive. It costs a lot of money to run clinical trials. I've been involved with trials where it was $1,000 per patient, right? Because you're doing MRIs or you're doing expensive medical tests and things. Checking your heart rate didn't cost me anything. That's why I did that one instead of giving you surgery or something. But suppose there was $1,000 per patient here. This study cost me $10,000 to run. This one cost me $5,000, and it's a more powerful design. So crossovers are much better designs if they work. You can't always use them, and we talked about this back in chapter 4. But if you are studying some kind of a treatment that changes the disease, then you can't use a crossover. Now that could be said to be true here. When I make you stand up and I check your pulse, and then I cross you over to the sitting group and I check your pulse, it's possible that the elevation in your heart rate isn't gone right away. That's called carryover of effect. So to make sure it's gone, I have to make sure you're seated for at least 5 minutes before I take it. That's called a washout period. Now you didn't notice that happening, but I stalled long enough in between that I knew it was at least 5 minutes since I checked your pulse the first time. So we're okay. Now, we don't even need to do it, but if you wanted to, take the other 5 differences and add them to the bottom of L3 and rerun this test using all 10 people. Since we actually have those observations, there's no reason to throw them away. Go ahead and put these 5 at the bottom of L3. Leave the 5 that are there and just go down and put them in, and then do the t-test again using L3. And I won't do it up here on the screen, but I will write down the new test statistic and p-value. As soon as somebody gets there.
T, I got it.
You got it? So what's T?
4.92,
4.92.
and the P is 4.13 to the negative 4.
So 4.13 times 10 to the negative 4. So I'm going to write it out as a decimal. That's 1, 2, 3 zeros, 4, 1, 3. So it's an order of 10 magnitude smaller than the p-value with only 5. So we doubled our number of patients and we got 10 times smaller p-value. Notice also that the t-test statistic got bigger. And what is this a measure of? 4.92 what? Standard errors that our data was away from the null hypothesis. And that's a lot. It's almost 5 standard errors. So you get a really small p-value. Okay? So the strategy for dealing with means problems and paired samples. You take the difference within each pair, then you put those differences in a list, and you do a 1 sample test or a 1 sample confidence interval on those differences. Okay? Now I just mentioned confidence interval, and that reminded me, oh, I haven't talked about confidence intervals yet. So how are we going to do a confidence interval for the difference? Well, you should still have in L1 and L2 your original 2-sample experiment, right? So you're going to use 2 samp t int on that one. So let's do that. We're going to do it the bad way first, and then we're going to do it the more powerful way. So 2 samp t int on L1 and L2. And what we're doing is the difference between them. Before you tell me what the confidence interval is, you should be able to tell me, is that confidence interval going to contain 0?
No.
This is the two independent sample ones.
What do you want the confidence level?
95.
It shouldn't, but it probably will.
Did you get your interval, Amy? What is it?
Negative 7.464.
Negative 7.464.
23.464.
23.464. Like that. Okay? It contains 0. What is significant about that? It fails to reject the null, which I erased. Well, I guess it's still over here. So we don't have sufficient evidence to say that the null is false because the null of 0 is plausible. Now what's going to happen when we do the difference using L3? What about the width of the confidence interval?
Smaller?
It's going to get smaller, right? Because you have much less variation. Because now you've come down to only variation within a person, not variation between people. Okay? So do the T interval on L3. Use L3 and do a T interval. 4.5374
And 12.263.
12.263. Interpret that interval for me.
Doesn't contain 0.
It does not contain 0, therefore
Can reject the null.
we can reject the null and say there is a difference. And the fact that both endpoints of the interval are positive tells me the difference is positive. Knowing that I did the subtraction stand minus sit tells me that standing heart rate is higher than sitting heart rate. Just the fact that every plausible value is positive tells me that standing is higher than sitting. Okay? Look how much narrower this interval is than this one. 23 minus a negative 7 is about 30. And then add that in, we've got about 31 total width of this interval. Right? That's 2 margins of error. Margins of errors? I don't know. This one's how wide? Well, about 12 minus about 4. This one's about 8. So from about 31 width to an 8 width on the same number of people. This used 10 people. This used 10 people. Much, much more powerful design. Okay, I've only got about 10 minutes or 5 minutes left, but I wanted to look back at the homework set. So look at problem 1048 real quick. And I didn't in advance pull it up on the e-book, so I can't show it up here, but so I'll read it to you. It says, of course, I pick these all the time. Refer to the previous exercise. Previous exercise has 3 before readings and 3 after readings, and it's exercise help blood pressure. So they took blood pressure readings for 3 people before they started an exercise routine, and then after 6 weeks or whatever, then they rechecked their blood pressure. So you have a before and an after. Is this independent samples or dependent samples? Dependent. Paired observations. Each blood pressure can be paired with another because they came from the same subject. Okay. Then it says the output below shows some results using software to analyze the data with a significance test. And it kind of bothers me that most of his problems in here, at least half of them, do that. They don't have you work the test or the confidence interval. They just show you some results and say, interpret this. Well, trust me, on the exam, you will have to do it. So it's a good thing to use your calculator and confirm that, yeah, I get the same p-value they got, or I get the same confidence interval that they got. Okay? So look at this, and I'm going to make some room here. And this is typical of a test question that I might give. Only I wouldn't give you the test results, I would make you do it. But what they have is a little table that says before and after, and then it has n, and that's 3 each. Then it has mean, standard deviation. He also has standard error of the mean, but I don't need that for what I'm going to do, so I'm not going to write it. 150, 130 are the means, and standard deviations are 15, 10, and then difference. Now, if all you've been given are summary statistics, you can still get the difference, because mathematically, if the data is paired, the difference in the means is the mean of the differences. Huh? Let me say it again. Difference in the means, x bar 1 minus x bar 2, is the same as the mean of the differences. So if I take all the individual differences and get x bar sub d, that'll be the same. Okay? So you can still get the mean difference. What is the mean difference? 20. Right? And I've got 3 differences that got averaged. Okay? The standard deviation of the difference, oh man. I was starting to say that does not work for standard deviations, but it looks like it does, and this is coincidence. Don't think standard deviation 1 minus standard deviation 2 gives me standard deviation difference. It's just bad luck on an example problem here. But this number you cannot get by subtraction. You must have the individual differences in order to compute the standard deviation of those differences. Yeah?
Wouldn't the difference between n be 0?
I'm not taking the difference. This doesn't mean difference of the n's. You're right, it would be 0, but this is how many differences did I have. And I had 3 people with befores and afters, so I had 3 differences. So the sample size is the same. Yeah,
So did they give you the standard deviation, or did you?
they
how did you
did.
do
This is given in the table.
that? Okay.
To get it yourself, you would use from the previous problem. They give you
Give you the data.
they give you the data. 150 to 130 for the first person, and the second person is 165 to 140. And you compute the differences, do standard deviation of those 3 differences, and it would have been the number 5. So I'm going to write over here as a little reminder, not S1 minus S2. That was coincidence. Okay? So, if I ask you to do a hypothesis test checking for a difference between before and after exercise, what would you do? And this is the biggest source of missed points on the final, is making this mistake, because they give you this data and you have enough information to do either a 2-sample t-test or a paired t-test. You pick the wrong one and it's invalid, and you just lost 10 or 15 points. So you really need to practice knowing whether this is paired data or not. Right? Now here we know it's paired data. We've already said that. So what do we do when it's paired data? T-test on the differences. So all of this, ignore.
If it's paired data.
If it's paired data, use that. Okay?
On the T test.
Exactly. So go ahead and do that test. The null hypothesis is the same. Mu d equals 0. And did they give me a direction on It says versus not 0. I had to read the software output. T-test of mean difference equals 0, and then in parentheses versus not equal 0. So we know it is a two-tailed test. So select that. So how are you doing this on your calculator? You go to T-test. Do you have stats or data? You have stats this time. Then you select stats, and then mu sub 0. The next thing that's on your screen is mu sub 0. So you select stats. What do we set mu sub 0 at? 0. That's the null hypothesis. This little sub 0 means the mean from the null hypothesis, and that's a 0. Next thing it wants is x bar. What's x bar? 20. Don't use the ones up there where I said ignore. Sx is a 5, and n is a 3. There is no pooled question for a one sample problem, so then you just go down and hit calculate, and tell me what you get for a test statistic and a p-value.
6.93 and 0.02.
6.93? That seems huge, 6.93, and 0.2 does not seem that small. But why is it 6.93 so big only has a p-value of that? Because we only have 3 subjects. The sample size is so small, that t-distribution is really spread out. Okay? So confidence intervals, use t-interval. Hypothesis test, use t-test on the calculator. Take the differences first, then work only with the differences. Good luck. We'll see you on Friday, I guess.